In this video, I want to briefly go over the realistic op-amp model. So the figure to the right is a more realistic model of the op-amp. So if you remember from before, if I want to draw the schematics, we had positive VCC here, we had negative VCC here, and then we have the positive or negative inputs, or more specifically the non-inverting and the inverting inputs, and then finally we had the outputs here for the op-amp. So we did some assumptions when we wanted to come up with these constraints that we had. So we said that for Vn to be equal to Vp, basically we should have a very, very large gain, right? But having a large gain, it doesn't necessarily mean having an infinite gain, right? So we basically did some simplification or some, you would say, assumption that for the voltages that we are usually using, having a few millivolt difference is not a big deal, right? But in reality, since you work with a real component, this gain may not be always tens of thousands, right? So it can be, let's say, 1,000. So in that case, a few millivolt difference may turn up to be a few tens of millivolts. So that makes this assumption to be not completely true. On the other hand, this Ri, the input resistance, we assume it to be very, very large. We said in the orders of mega ohms, right? But even if it is in the orders of mega ohms, that doesn't make Ip and In to be completely zero. It is zero when it is infinite, or if these two are open circuit, right? But this is usually not the case. Also, another assumption that we usually make when we design op-amp circuits is that this Ro, we assume it to be zero. But in reality, it is very small, but not necessarily zero. So this is a more realistic model for the op-amp that is very common to be used in practice. So any circuit that you have, you can use this model as well and come up with a more accurate equation for the gain. But of course, since in this model we have this additional resistors that we usually don't account for in the simplistic model, and also we have this voltage controlled voltage source here as well, the calculation is going to be a bit more complicated than what we already discussed so far. But nonetheless, you can use the same concept that we have discussed before, the node voltage method, the mesh current method, and all those other simplifications to come up with the solution for any circuit that uses this more realistic model. So let's say I did that for the inverting amplifier. I highly suggest you go through the steps yourself, but that is only a representative example of when I say equations can be a little bit more complicated, what I mean by that. So if we are designing an inverting amplifier using this circuit, if you remember, for the inverting amplifier we had to have a feedback resistor between the output and the inverting input. Then we had this Rs, which was connected to a voltage source and then connected to the ground, so this is Vs. Also we had Vp to be zero, or the non-inverting input to be connected to the ground. So based on the simple equation that we had for the inverting amplifier, VO would be negative RF over RS multiplied by VS. So this was based on all of the simplification that we had done. But if I eliminate those simplifications and work based on the model that I have, this is the equation that I get for the gain of the inverting amplifier circuit. As you can see, A appears in multiple places. We also have Ri appearing and also Ro appearing in the equation, right? So I highly suggest you go through the steps, rewrite or redraw this circuit in a more meaningful and visually pleasing manner, and then try to do node voltage analysis for the nodes that we have here, and then come up with the equation that shows the relationship between VO and VS. So now that we have this, let's just see how changing the different variables that we have and making it closer to the ideal case has an impact on this equation. So one thing that we assumed was Ro to be 0. So if we assume Ro to be 0, then this term equals 0, and also this term equals 0, and also on top this becomes 0. We also assume that our I goes to infinity or is very large. So assuming that our S over our I becomes very, very small in comparison to this one which is summed with, right? So if we do that, this becomes also 0. So now in the numerator we have only negative A. In the denominator what we have is so if I assume Ro to be 0 and Ri to be infinity, VO is going to be negative A divided by Rs over Rf multiplied by 1 plus A plus 1. So the last condition happens when A goes to infinity. So when A goes to infinity, 1 plus A is almost approximately A, right? Infinity, or a very large number multiplied by Rs over Rf, it's going to be greater than 1, right? So this becomes negative A over Rs over Rf multiplied by A. But now if we eliminate these two A's from top and bottom, because they are very close, right? So even though we made some simplification, let's say if A was 100,000, the numerator and the denominator coefficients that we have here are very, very close to each other, right? So even though we had to, let's say, eliminate this one or eliminate this one, so they are very, very close. So if we do that, then we end up with negative 1 over Rs over Rf, or if I rewrite it, it's going to be negative Rf over Rs. So as you can see, even if we start with the more realistic model and come up with the equations, as soon as we start applying those simplifying factors to the equation, the final equation is basically what we got before. So in this video, we briefly went over the more realistic model of the op-amp, and we also saw how introducing the more realistic model can provide some insight on how simplifying factors that we have used before can help us in solving op-amp circuits.